So let's look at the following example that deals with Archimedes' principle and specific gravity. If the specific gravity of ice is 0.92 and that of seawater is 1.03, calculate the percent of an iceberg that is below water. So let's suppose our surface of seawater is shown with the following blue line. And our iceberg is shown to have the following shape. So let's assume that the iceberg has a larger percentage of it below seawater than above seawater. So that means our diagram looks something like this. So we begin by assuming that our iceberg, the object, is in static equilibrium. In other words, it's floating and a portion of the iceberg is floating above the seawater. So if the iceberg is assumed to be in static equilibrium, that means the sum of all the forces acting on the iceberg along the y-axis is 0. So we have two forces acting on the iceberg. We have the force of gravity, which is pulling the iceberg to the bottom of the ocean, and we have the buoyancy force, or the buoyant force, that is acting to push the iceberg out of the water. And these two forces must have the same exact magnitude because our object is assumed to be in static equilibrium. So, the sum of all the forces acting on the object along the y-axis is equal to 0. We choose the upward force to be positive, downward force to be negative. So the force due to the buoyancy of the object, or the buoyant force, minus the gravitational force is equal to 0. We bring this force to this side and we see that the two forces must have the same exact magnitude. Now, the force of buoyancy is simply equal to, according to Archimedes' principle, the mass of the seawater that is displaced by our object multiplied by the gravitational constant g. And that is equal to the mass of the iceberg multiplied by the gravitational constant g. So, notice that the mass of the seawater is simply the density of seawater multiplied by the volume of the seawater that is displaced by our object. So this entire volume, this entire portion that is below our seawater is the volume displaced. So let's represent that with V displaced. And we multiply that by the G. This is equal to the density of the ice multiplied by the entire volume of the ice, including this top portion. And let's represent that as V iceberg and multiply that by G. Now notice the G's can cancel, and if the G's cancel and we rearrange our equation, we get the following result. The ratio of the density of the ice to the density of the seawater is equal to the volume of our seawater that is displaced, which is equivalent to the volume of the portion of the iceberg that is below seawater, divided by the entire volume of the entire iceberg. And in fact, this ratio is exactly what we're looking for. This ratio will give us the ratio of the iceberg that is below the seawater. And if we calculate the ratio and multiply by 100, that will give us the percentage of the iceberg that is found below seawater. Now, how exactly can we calculate the density of ice to the density of seawater? Well, we're given that our specific gravity of ice is 0.92 and the specific gravity of water, of seawater, is 1.03. Recall the formula for specific gravity is simply the ratio of the density of the fluid to the density of water, H2O. So if we take the specific gravity of ice and divide it by the specific gravity of seawater, we get the following ratio. And notice this quantity appears in the denominator and also in the numerator. So these two quantities will cancel and we'll get the following result: the density of ice to the density of seawater, which is exactly what we're looking for. So we plug in 0.92 for ice and 1.03 for our seawater. So this quantity, and that's equal to this quantity, which gives us the volume displaced divided by the volume of the entire iceberg. And this quantity is about 0.89. So now we take this quantity and multiply it by 100%, and we see that approximately 89% of the entire iceberg is found below the seawater, and only about 11% is found above seawater. So we can only see 11% of that iceberg.